All right, so we're going to continue our talk about population ecology, moving away from the dynamics of populations, now talking about population growth and the patterns of growth and rates at which expansion occurs. All right, so when we talk about populations, populations have characteristics that emerge from the collective group of individuals that comprise it per se. And population growth, when we say growth, it doesn't necessarily mean a positive growth, which would be an increase in number. Population growth, again, can go in both ways. You can either have positive growth or negative growth. So population growth or decline, again, either that positive or negative aspect, is one of these emergent properties of populations. Right? We can take the Galapagos cactus finch, which is pictured here, Geospiza scadens. This specific species has such a high reproductive rate. The reproductive rate is actually over 2. It's like 2.1. And that means the population can more than double its size each generation. So kind of looking at the actual aspect of population growth and the different factors that allow for variations in reproductive rates and therefore variations in the rate of growth. Now, population size fluctuates in all types of environments, whether it's a terrestrial environment or an aquatic environment. Kind of looking back at the previous lecture, we had looked at the factors that influence the rate of change in populations. Now we're going to instead focus more on the specific factors that determine population growth, specifically how the environment can act to influence growth based on aspects of resource availability. Now, different growth patterns arise depending on those factors, and that or the influence of these factors operate on birth and death rates. Now, population's overall growth rate, or the change in population size, which is noted as delta n, per unit time, which is noted as delta t. This is delta n, this is delta t, is a function of birth rates, death rates, immigration rates, and emigration rates. Those major factors of change that we had talked about in the last lecture. So when you're determining population size or the overall growth rate, it's merely a function of delta n divided by delta t. This triangle is the Greek symbol delta, which means change. So in general, this equation is used to measure growth. And it's a way to determine population changes over a specified time span. That can be a year, decade, etc. So the internal factors or variables that serve as your delta n and the delta t, basically what this is equaling, yes, it equals population growth. More specifically, it's an aspect of births minus deaths plus immigrants minus emigrants. So taking into consideration those aspects of population addition and population subtraction factors. Now, if no immigration or emigration is occurring, right, if we had a closed population that we were considering, then delta t over delta n over delta t is simply equivalent to births minus deaths. So the difference between the birth rate and the death rate per individual, we talked about this in the last lecture, that is called the per capita rate of increase, which is little r. So little r per individual is equal to delta n over delta t. All right, so we're going to talk about some different patterns of population growth. In general, there's two patterns or kind of growth curves that growth can follow. One being exponential growth, the other being logistic growth. Exponential population growth occurs when R doesn't change over time. But even though R is not changing over time, the instantaneous growth rate increases as population size or number increases. So we'll use somewhat of a different measure, right? For in general population growth, it's delta N over the component of delta T. Instantaneous population growth uses this formula here, where you measure the growth by little d big N over little d T. And these are rates since they reflect changes in number over a period of time. Another component about exponential growth is that the population size does not limit growth rate. So this means it is density independent. In nature, generally, this pattern of population growth, as far as exponential growth, is common in one of two circumstances. First being a few individuals colonize a new habitat that has a plethora of resources that are available for utilization. The second circumstance is a population has been devastated by some sort of disaster, either a storm or some natural disaster event. And as things begin to recover, you form this new population that starts with only a few surviving individuals. So it's more of this regeneration following a successive occurrence or following a successive pattern. Now, exponential population growth in general is an unrealistic or quixotic situation for most organisms in the natural world. In this growth scenario or pattern, there are no environmental barriers to growth. So growth is set to occur at its maximum rate. And again, that's unrealistic because very rarely do you find a situation where growth is occurring in a population that has no limit to its growth potential or is occurring in a environment with unlimited resources. So, for example, unlimited food, water, space. Ultimately, populations growing in this way must crash as they run out of resources. Some natural populations will follow continual exponential growth and crash patterns. And that's kind of the overall life cycles that are repeated for each generation. These species are called R strategists, since evolution has shaped them to maximize their intrinsic rates of increase. So these include fast-growing species such as insects, weeds, even some marine invertebrates. When we look at the exponential growth curve, it's typically described as being J-shaped. At the beginning, this very slow rate of increase, this is called the lag phase. So there's only a few individuals. You have this very slow period of slow growth that's occurring. And then you reach this sudden turnover period where you move immediately into the exponential phase, where you have rapid increase. And this is because there's access to unlimited food, water, space, maybe there's no predators. So the population is able to exist at its full reproductive potential. All right, so this is just a little practice problem to go through, basically putting that instantaneous growth rate function into play, right? So what is the instantaneous rate of population growth when, say, birth rate is equivalent to 50 deaths per 1,000 individuals per year, right? And the death rate for that same population is 20 deaths per 1,000 individuals per year. And the starting population size is 1 million individuals, right? So the formula, again, is dn divided by dt. just another way of saying the change in n divided by the change in t. So for this, we want to look at basically taking the difference between your birth rate and death rate per population size. Again, our size is starting at 1 million individuals. So here we would have 50 divided by 1,000 individuals, right? That's our birth rate, minus 20 minus 1,000 individuals. That's the death rate. You take that value and then you multiply it by the size of the population, the 1 million individuals, right? So that's going to end up giving us a value of 30,000 individuals per year. And that's how you can kind of work out or calculate the instantaneous rate of population growth. Now there's one of two equations that we can use to calculate exponential growth. There's an integrated form and a differential form of the equation. So this is, again, the general equation that's used. The integrated form of the equation, so this allows you to measure or calculate the population size at any period of time, so any time value. And you can calculate this through the formula here, NO times e to the power of RT. Here, R is more specifically represented by a value called Rmax, which we'll talk about in a moment. But in this form of the exponential growth model, NT is the number of individuals at any value of time, time being, again, t. And O is the number or the initial number of individuals, so kind of what you're starting at. E is the base of the natural logarithms, and then R max is the intrinsic rate of increase, and T obviously is the time variable or the number of time intervals. So this equation kind of at its roots is very similar to the geometric equation that we had talked about for geometric growth. But in this form, E to the power of RT is essentially replacing that value of lambda. Now, if ecologists are instead interested in understanding what is happening to populations following continuous population growth in an unlimited environment at a given moment in time, they can calculate instead what's a variant form of the instantaneous growth rate. This we call the differential form of the equation. So here, that dn over dt value, right, that equals Rn. Rn is further equal to birth rate minus death rate for a specific value of individuals at a moment in time. Now, this exponential growth equation expresses the rate of population growth, which is the change in numbers per time, as the specific value that's called the per capita rate of increase, which is R max times population size, N. Now notice the per capita rate of increase that's used here. It's not that individual R value that you've seen before. It's actually slightly different. This is an R max, so it has the subscript max to it. It is different from are. They are two separate things. A lot of times people will talk about them inversely or kind of as the same entity, which is incorrect. They are two different things. The subscript here indicates the maximum per capita rate of increase that can be attained for a species or a population under ideal environmental conditions, right? So this would be achieved by a species where birth rates, death rates, and age structure are all constant. So you have ideal growth rates that are occurring. Under these optimal conditions, right? So again, where RO is as high as possible because birth rates are as high as possible and death rates are as low as possible. Your original R value, that original intrinsic rate of increase, reaches the maximal rate of natural increase, right? So this rate becomes realized and is designated as R max. And again, that's because your per capita rate of increase has attained those maximal growth rates. So you can call this either the intrinsic rate of increase. I usually refer to it as the maximal instantaneous rate of increase per head because it allows you to better differentiate or disassociate the two from one another. Now your Rmax is inversely related to generation time. This maximal instantaneous rate per head, it also varies among animals by several orders of magnitude, as you can see in this table that I've included here. Small, short-lived organisms such as E. coli or Escherichia coli, which is a common human intestinal bacterium. They have relatively high R max values. As indicated here, you can see their growth rate is very high relative to some of these others, right? Whereas kind of comparing to these larger, longer-lived organisms, such as humans, for example, we have comparatively very low Rmax values. And again, the components that are influencing or contributing to this Rmax value is the instantaneous birth rate per head, so B, as well as the instantaneous death rate per head or per individual, D, under those predicted optimal environmental conditions, right? And the rates of reproduction and death rates, they evolve in concert, right? So when either one is high, the other is usually low, right? So if you have very high birth rates, usually that's balanced by relatively low death rates. Or if you have high death rates, you have low birth rates. So they're usually inverses of one another. Now, again, depending on those environmental conditions, your Rmax value will change. It can either be a positive value. You can have a negative value if the death rates are greater than or surpass the instantaneous birth rate per head. You can also have positive R values. In this case, the positive value or positivity is occurring because instantaneous birth rate exceeds death rate. So you have more individuals coming into the population and therefore allowing for population growth rather than population decrease because of a higher death rate. Now, because even when we're considering exponential population growth, even in that case, Because natural populations are usually subject to factors such as disease, competition, so forth, the actual per capita rate of increase, so again, that realized R, so just that little R value, in general is less than the R max value, which should make sense. Again, the R max value is that predicted maximal rate of increase under optimal conditions. In general, conditions are never in that realm of optimal conditions. So as a result, the realized value, the true R value is, okay, sorry about that. I had to quickly blow through that real quick. So I ordered pizza. I'm hungry, so had to go retrieve the pizza. But anyway, what I was saying before, again, in general, that realized R value, the little r, is going to be less than R max. So when we're looking at the exponential model, you can actually think of the R max value as being more of this constant value, while n, the number of individuals, more of the variable that's being tested, right? So as population size increases, right, as n increases, the rate of population increase, right, the dn divided by dt gets larger and larger and larger. And that rate of increase in general gets larger because your R max value, which is now serving as a constant, is going to be multiplied by that continually increasing number of individuals, right? So again, your R max and that little r value, they are two separate things, right? R max is what could be obtained under ideal conditions. The true rate of increase, or the actual or realized rate, that is little r. Right? Now, at any specific time, the instantaneous growth rate, little r, so we're talking about this guy now, will tell you what that population is doing at that moment in time. And again, R is usually less than that R max value because your conditions, your environmental conditions, are rarely optimal. So even kind of going back to this previous slide, right? So even though we consider the R as being more of this constant, exponential growth adds an increasing number of individuals as that total number of individuals, or total population size, n, gets larger, right? So if R equals, let's say R is a value of 0.02, right? And let's say n, your population size, is equivalent to, we'll go with even 1 billion individuals, then over 20 million individuals would be added to the population in a year, right? You compare that to if you had the same rate, so same R value, but a far smaller population, say a population of only 100, you would have just 2 individuals added in a year. And in general, you read these values the same way. So whether it's the R max or the R value, they're read or interpreted the same way, right? So if there's more births than deaths, the population is growing. You'd have a positive R value. If there are more deaths than births, it is shrinking, right? You usually have a negative value. And if the birth rate equals death rate, then your R value is going to be equal to 0. And that means the population size stays the same. Now, as I was saying before when I was initially talking about exponential growth, in reality, you don't have populations existing in environments of unlimited resources, right? In reality, populations are dependent upon finite resources for survival. And this will limit that exponential phase of growth for a specific population curve. And we basically refer to this as all environments having this finite carrying capacity, or K. Now, beyond this limit, the population can no longer increase in size overall. So as population size increases, growth rate will eventually slow and then cease and start to taper off as the population levels off, right? Now we call, or this pattern of growth, I should say, produces what's called a sigmoidal or S-shaped population growth curve, where the population growth is limited by the carrying capacity, or K. K represents the maximum number of individuals of a species that an ecosystem can continually supply resources to. Now, that carrying capacity is not fixed across time. It will vary among species, vary across populations, and also vary across measures of time as you have changes in the availability of resources. Now, the actual value of K, it's influenced or determined by population density and largely, but also a suite of other specific limiting factors, as they're called. Limiting factors are environmental factors that control the maximum rate at which a process can actually occur in the environment, right? So, for example, population growth, it controls the maximum rate at which population growth can occur. Now, some of these factors, these limiting factors that contribute to the K value, are things like food and water availability, space for territories and nesting, the availability of mates, disease, predation, right? All of these factors that I have listed here. Senescence is another one. Senescence refers to the death from age-related illnesses. Now, this entire pattern or overall pattern of population growth is called logistic growth. Logistic growth is density dependent, right? So exponential growth was density independent and wasn't influenced by specific population size. Logistic growth is influenced by population density, so it's density dependent. And as a model, it acts to account for the patterns of growth shown by populations as they deplete environmental resources, largely as they continue to grow. So the logistic growth equation, which is pictured here, is the equation that is used to describe logistic population growth. It's essentially, if you look at it, this modified version of the exponential growth equation, right? This whole portion here is the same as the equation that we saw before, but it contains this little added component, right? This added component represents a way to show slowed growth as population size approaches its carrying capacity. Now, if population size, right, that value of n, capital N here, if that is below the carrying capacity, K, the population should continue to grow. When the population density gets very high, the population's per capita birth rate will decrease, and that causes an increase in the per capita death rate. And as a result, you have declinations in R values. Now, these are the specific phases of the logistic growth curve. All the phases can be explained by relative rates of natality or birth, mortality or death, immigration and emigration. Right? So you start off with a lag phase, and then you reach this point of biotic potential where you move into an exponential growth. Right? So this rapid growth in population as resources are used, and then you go into this deceleration as those resources begin to become depleted and you near the equilibrium phase. And here the population will stabilize. All right, so in the logistic growth model, the realized per capita rate of increase, which is essentially R equals R max times 1 minus N over K, which is equal to R max minus R max times N over K. That depends upon population size. As I said before, logistic growth is density dependent. So therefore, when the population size, N, is very small, the per capita rate of increase is approximately or roughly equal to R max. And as that N value increases, the realized R value decreases until that N value is equal to K. And at that point, the realized R value is 0. So again, it's working, or the population growth movement is moving towards that stabilization based on the population size. So the relationship between realized R and population size in a logistic growth model generally follows this straight line that is shown here, right? So when N is small, the K minus N over K value is close to 1, meaning the growth rate would be high. And if your N value is large, that K minus N over K value gets smaller. And it usually moves in this trend until these values equal 0, at which point your growth will stop. And you can understand this again thinking of what that little r value represents, right? You can again remember or think that r is equivalent to or represents the difference between birth and death rates in a population, right? So thinking about it in this figure, at a very low population size, the per capita death rate and the per capita birth rate, B, greatly exceeds your per capita death rate, D. As that population size increases, the differences between those two variables, between the per capita birth rate and per capita death rate, will decrease. And that can result from decreased birth rates. If you decrease birth rate, you increase death rate. It can also result from simply that increased death rate, or it can occur from a mixture of both. Once the population reaches K, so you have that intercept there, meaning population size has reached its carrying capacity, the difference between your birth rate and death rate will be equivalent. So birth rate equals death rate, and that means that difference equals 0. As a result, your population growth stops. So in a hypothetical population, density-dependent growth has 3 distinct stages. So as I talked about before, initially the growth is exponential, right? Your R value is constant, so you have this rapid growth that occurs as individuals start accessing those nutrients. Growth rate begins to decline as that N value increases. So your population size continually increases, and as such, that growth rate begins to decline. right at this declination stage, when competition for density-dependent factors begins to occur. Right? So you've started to use up those resources, and as a result, they are now maintained in limitation that's going to have impacts on the size of the population. If the population is of a very large size, that limited availability of resources is obviously going to have a much larger effect on population growth going further. So moving from this declination stage, you'll have some growth until that growth rate reaches zero. Right? You'll reach zero once the population size reaches its maximal level. It reaches carrying capacity. So essentially, the N versus T perspective per se is flattened. So it's held in equilibrium here. So comparing the two, exponential versus logistic growth. Again, exponential growth is occurring when you have unrestricted environmental resources, or growth is unrestricted because you have infinite availability of resources, whereas logistic growth is restricted or bound because your resources are held in finite availability or finite number. So the logistic model of population growth, while it's valid for many natural populations because it models more of a realistic view of natural populations, and it's useful in that sense as a model, it is in multiple aspects what you can say a simplification of the real world population dynamics. Implicit in the model is this notion that the carrying capacity of an environment doesn't change, which is not the case. As I mentioned before, the carrying capacity varies frequently. It can vary on an annual basis, a seasonal basis. Right? For example, some summers are hot and dry, whereas others are cold and wet. In some areas, the carrying capacity during winter may be far lower than it is during the summer. You can also have natural events that occur, right? Earthquakes, volcanoes, fires, that can alter the environment, and by altering the environment, you can alter those limited resources and therefore the carrying capacity of that environment. Also, you have to recognize that populations do not usually exist in isolation, right? We talk about gene flow and interrelationships between populations. They engage in interspecific competition, for example, right? That is, they share the environment with other species, competing with them for the same resources that are held in these finite populations. And recognizing these factors, right, is important to understand how a specific population will grow, with the understanding that that carrying capacity at any one time can change, again, within certain seasons, within annual changes. Even generational changes can shift or find shifts in carrying capacity. All right, so what factors limit population size? Nature regulates population growth in a variety of ways. Kind of simply put, or in general, they are grouped into two categories, or two bins, right? There are density-dependent factors, in which the density of the population at a given time affects growth rate and mortality. And then there's density-independent factors, which influence mortality in a population regardless of population density. Now, kind of implying this to the realm of conservation biology, conservation biologists will recognize both types of factors. And they want to understand both types because by doing so, it helps them manage populations in an attempt to prevent extinction or population, and in general see how the presence or absence of certain factors may influence growth. All right, so looking at your density dependent factors, right? So again, these change in intensity as a function of population size. Most of them are usually biotic factors. In general, we see these factors as being responsible for the declining growth rates that occur in logistic population growth. So these are factors like disease, predation, competition, right? They can all decrease aspects of survivorship, fecundity, even both. And the effects of these factors intensify as the population increases in size, right? So think about disease, for example. In general, you see the spread of disease increase in kind of pathogenicity rate, or the rate at which it will infect other individuals as you increase the density of population, right? So when you look at denser populations, usually diseases will spread far more quickly through that population than, say, a population that maybe had the same number of individuals but was more distributed across environments. So because you increase that area, you decrease the density. A lot of them, the factors, are based on intraspecific interactions or interspecific interactions. Intraspecific interactions refer to within a species. So these are interactions that are occurring between individuals of the same species. So example would be competition among members of a cohort for food. Interspecific competition or interactions, these are between species. So individuals of different species interacting with one another. This would be predation, parasitism, or competition among species for food. So again, a lot of these drive or serve as the foundation for those density-dependent factors. And again, those changes that they cast in survivorship and fecundity will kind of spur logistic population growth and therefore define that habitat's carrying capacity. Now, this is slightly different than density-independent factors. Density-independent factors such as variation in climates or weather patterns, most of them are abiotic. And they operate by changing birth rates and death rates irrespective of population size. So regardless of what the population size is, or regardless of the population's density, they will exert their influences on that population. So that's why we refer to them as density independent. The effect of that factor on the population doesn't depend necessarily on the growth or the size of that population. More specifically, or kind of on the other hand, it actually depends specifically on the size of that population at that time, right? So what is the population at that time? And that, based on that size, will monitor the actual effect that factor will have. But the function of that factor on the population isn't going to be driven or affected by population change over time or in the future. So again, these are most of your abiotic factors. So weather is a large one, climate change, even changes in soil nutrients or cycling patterns.